Additional instruction for assignment 132, Introduction to Ka values. This top part is important here. It talks about Ka measuring a ratio, which is shown in this corner here. So you have a weak acid. In this case I'm using HX. It can dissociate in water to produce these ions, H3O plus, X minus. It's a reversible reaction. So we'll get this equilibrium produced where some are here in the dissociated state, the ionized state, and some are here in the HX state. With a weak acid, it always ends up being most is in the HX state. The reason I know that is because Ka values measure this ratio. And you can see the Ka numbers are quite small, 10 to the minus 4, 10 to the minus 5, 10 to the minus 7, which would mean that the number on the top is small and the number on the bottom has to be big. So I know there's not many. Maybe it's better to say few here instead of some. Few are in this dissociated state, most are in this associated state. That's how I get a Ka ratio that's such a tiny number. About 6.4 times 10 to the minus 5 is 4 zeros and then a 6, 4. And I'm hoping when you look at these two values, you can see that this is the larger one. 10 to the minus 4 is bigger than 10 to the minus 5. Question number 2 is talking about using arrows to represent an equilibrium that may favor the left or the right. The text says that nitrous acid is a stronger acid than acetic acid because the Ka is bigger. The numbers here show that the percent dissociated will be smaller for the acetic acid, only 1% dissociated. The nitrous acid is 2% dissociated. We can represent this perhaps more easily with arrows. 2% dissociated means 98% associated. So 98% is here. 2% is here. That's an example of the few. To represent this equilibrium with arrows, I'll have a tiny arrow going to the right and a relatively large arrow going to the left. This should suggest to you an equilibrium that favors the left side. The HNO2 plus water is the more stable state. 98% will be in that state, but 2% of the population will be in this state. In the second equation, we have only 1%, so this is a weaker acid. It has a smaller Ka value, so there's less dissociation at equilibrium. To represent this one, I'll draw an even tinier arrow to the right, and a nice big arrow going to the left, trying to represent that there's only 1% here, and 99% here. Question number 3 is asking you to think numerically what must be true. The key is to recognize the ratio of the H3O plus and the F minus, the dissociated form, over the HF is equal to 7 times 10 to the minus 4, which is a very small number. So this on the top is small. This on the bottom is large. And that is what makes the ratio be this 7 times 10 to the minus 4. So the words that express that is this: HF molecules are vastly more numerous, perhaps on the order of 97 to 3, something like that. Last question on the page here is saying that do not make the mistake of saying the HF is a strong acid. It is far from strong. This suggests that hydrochloric acid, the Ka value, if we were to put one, would be greater than 1,000,000. So 7.2 times 10 to the minus 4 is very, very, very small compared to 1 million. Here it's saying use appropriate arrows to illustrate the concept of the strong acid versus the weak. So HCl plus H2O, you've seen this before in the simulations. One-way reaction. The Cl minus will never regain the H plus. This is the boing, 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 fumbling ion. The HF, on the other hand, is a weak acid. This should remind you of the behavior of weak acids. It will dissociate a little bit. So a small arrow going to the right, it will reassociate readily. The balance at equilibrium for HF might be 3%. 97% is a reasonable approximation for what you would expect with HF dissociating in water.